In this video, we're going to answer the Unit 3 Chemical Bonding Study Guide. Before we start with the study guide answers, we want to cover some of the important things from middle school that are going to be seen on your test in the questions and application. So the first thing is, where are the different classes of elements? So we learned in middle school and in high school that we have metals, nonmetals, and metalloids. And there is a clear staircase divide on the periodic table to help us locate where those elements are. For instance, everything before the staircase line is going to be a metal. So we have alkali metals, alkaline earth metals, transition metals, and inside of the transition metals, the lanthanide and actinide series. Surrounding the staircase line is going to be 7 metalloids, and after the staircase line, we're going to have nonmetals. Continuing on the middle school trend, we learned that if I combine different combinations of these elements, then I'm going to get different types of chemical bonds. And that is where the high school part of this came into play. So M stands for metal and NM stands for nonmetal. If I have a metal combined with a metal, that would be an example of a metallic bond. If I had a nonmetal and a nonmetal, that would be an example of a covalent. And if I had a metal and a nonmetal, that would be an example of an ionic combination. So at the very foundation of all of these test questions, you should be able to go to your periodic table and see what combination of elements are there, and then answer the questions based off that combination. In high school,
May I have your attention, please? Javier Macklin, if you're in the building.
I'm going to bring that back up and repeat myself just a second because I can't remember. These are your basic combinations of what you should be looking for. Let's go ahead and talk a little bit more about covalent. So in high school, we explored that there are 2 versions of covalent. There is polar and there is nonpolar. Polar is going to be made up of different nonmetals. And because of that, Mother Nature will build the compounds asymmetrically. Now, if this is a new vocab word for you, asymmetrical, it basically means not a mirror image. So there are different things around the bond or around the central atom making it asymmetrical or polar. If it's nonpolar, then that is going to be an element or compound made up of the same elements, or the same nonmetals, I should say. And because everything is the same, then that is when we're going to have mirror images happening around the bond or the central atom. And Mother Nature designed these compounds as symmetrical. So remember, covalent is when nonmetals are joined together. But we now know that nonmetals join together differently. They can join together with different nonmetals, forming asymmetrical, uneven, unequal bonds. And then we can also have nonpolar, which would be the example of our same nonmetals, symmetrical, same element bonds. Remember, nonpolar is our element bond that is low, low, low. So it's low melting points, low conductivity, no solubility or no conductivity. And then ionic is our bond that has all of the things, right? It is soluble, it has a high melting point, it has a high conductivity, so on and so forth. Now let's go ahead and start to answer some of these study guide questions. So I'm going to run through these relatively quickly. I'm also going to highlight for you the things that I think are important. Maybe also write in some additional things that you're looking at or looking for so that you can label your test question examples as a chemical bond type. So if we are a good conductor when dissolved in water and we form ions, that's going to mean that I am an ionic bond. If I am a poor conductor, that is something that is low or no conductivity, and that would be an example of an NPC, nonpolar covalent. If I form a bond between two nonmetals, we know that that's going to be covalent, so you can put polar covalent and nonpolar covalent here. If it contains a sea of electrons, that is going to be an M, metallic bond. You definitely want to know what is happening with the electrons of every type of chemical bond, and sea of electrons is a phrase that we tie with metallic. This happens because the electrons are free moving, or we can also say delocalized. If we have a malleable and ductile substance, that comes from a metallic bond. So malleable and ductile is metallic. In this image, we can see that we have a plus and we have a minus sign. These two circles are separate from each other, which tells me that they are not sharing. If I see an image like this, I know that that is representing a transfer of electrons, and that would be an ionic bond. I'm going to jump over to the right-hand column where I have some extra space. So if I'm a good conductor when a solid, this is the key phrase right here that we think got you on the midterm when it says when a solid. That's going to be a metallic bond. If I have a bond between a metal and a nonmetal, then you know that that is a classic example that's ionic. And if I have a bond between metals only, again, classic example of a metallic bond. If I have a hard brittle solid at room temperature, the key phrase in here is a brittle solid. There's only two types of chemical bonds that give us a solid. That's ionic or metallic. And out of those two, there's only one that is brittle. That means it can break easily. That's going to be an example of an ionic bond. So this is I. If the electrons are shared equally, remember I said anything to do with the electrons is going to be super duper important. That's going to be a non-polar covalent bond. When we take a look at these two pictures right here, they were all over your midterm. They're going to be all over your test. These are going to show you sharing. Because the bubbles are touching. Now, what kind of sharing has happened? Here we can see that the bubbles are evenly shaped and equal everywhere. So we would say that they are being shared equally, which again is going to be our nonpolar bond. Here we can see that they are not being shared equally. So we would say share unequally. There's a difference in how they're being shared. This would be an example of a polar covalent bond. Now let's go ahead and take care of the last few examples in this, starting with shape. If it has a symmetrical shape, remember this means mirror. This means let's change that. This means even. Everything is the same. Then that's going to be an example of a nonpolar covalent. But if I have an asymmetrical shape, that means that everything is different. And so that's going to be a polar covalent. Water is an example. So water is H2O. That is going to be made up of two nonmetals, H and O. And since they are different from each other, then that's going to represent a polar covalent bond. Diatomic molecules. Di means two, atomic means atoms, and molecule means that they are bonded together. Two atoms bonded together and they're the same. So truly an example would be something like Br to Br, maybe H to H. You get the gist. But as long as on both sides of the bond, the dash in between the symbols, we're going to have the same atom, then we have nonpolar covalent, diatomic molecules. Go ahead and highlight this one because we're going to talk about this a lot later. Last two examples. So electrons move freely around each cation. The phrase here is electrons move freely. That's going to be very indicative of a metallic bond, M. Ions are locked in an arranged pattern. Now, this does not specify what kind of ions. what the electrons are doing. So in my brain, there can be two answers to this. The first answer is ions or ionic because we see ions. But also, if we have ions that are locked into an arranged pattern, this is a solid. So while it could be an ionic one, it could also be a metallic bond as well. Let's go ahead and take a look at question number 2. So questions 2 and 3 are asking you to do the same thing, but they look completely different from each other. I'm going to show you how to approach these questions, and then I want you to pause the video and try some on your own to see how you do. So let's take a look at combining cation A with anion G. This is the kind of question where knowing your positive and negative numbers on your periodic table are going to be so important. If we take a look at your periodic table again, we can place the positive and negative numbers across the top of the families. Anything in group 1 is going to be +1. Anything in group 2 is +2. Anything in group 13 is +3. And yes, we skip the transition metals because they could be multiple versions like +1 or +2. Anything in group 14 is going to be plus or minus 4. Group 15 is -3. Group 16, -2. Group 17, -1. And group 18 is going to get us to 0. We can basically take this same file and put it onto the periodic table that's been labeled as columns A through H. If I go to cation A, that would be +1. So this would be a +1. If I go to G, that's going to be representing the halogens. That's going to be -1. Once you know what the ionic charge is, the plus and minus number, you're going to pair them up with each other. Once you have them beside each other, you're going to check your total positives and total negatives. If they are the same number, cross them out, you're done, answer the question. If they're not the same number, build it out and then answer the question. When I take a look at these numbers, I have one positive and one negative. Those are going to be the same number, 1 and 1. So I'm going to go ahead and be able to cancel out those charges. That means I have 1A to 1G. So I have a 1-to-1 ratio. In the XY formula, that would be XY. If I do this with B and G, B is going to represent the alkaline earth metals, which have a +2 charge, and G is still a halogen, -1. If I put those beside each other, we're going to have to build it out before we can answer the question. Because I have 2 positives and 1 negative, I need to build on another negative, and then I have 2 positives and I have 2 negatives. I can then cancel it out. I can tell you that the ratio is 1 to 2, and that becomes X, Y, 2. Pause the video now, and then we'll talk about the answers. So here are the answers for the remaining 3 rows in blue. Let me go over them while you double check yourself. In row 3, we had A versus F. So that's going to be right here underneath the periodic table where you see my mouse wiggling. So we had A with a +1 and F with a -2 charge. That -2 came because right beside it, it was -1 with the halogens. Then when you compared them, I had 1 positive, 2 negatives, so I needed to have 2 positives to balance out the 2 negatives. I got rid of my charges. I had 2 A's and 1 F, creating a 2-to-1 ratio. That transforms into X2Y, and we move on to the next row. That can be seen up here where you see my mouse wiggling now to the side. So we started out with a B +2 and an E -3 based on its location. So we added on another B first, but then that gave me 4 positives and only 3 negatives. So I added on another E. Now I had 6 negatives, yet only 4 positives. So I added on another positive and I got to 6 positives and 6 negatives. I wrote B 3 times, E twice, 3-to-2 ratio, forming an X3Y2 pattern. Last but not least was C and E, +3 and -3. Plus 3 and minus 3 are the same number of pluses and minuses. So that means that they went ahead and canceled out and formed a 1-to-1 ratio with an XY formula. In the following questions, we're going to ask you what type of bond would form between the different groups. Your options are metallic, ionic, covalent, or none. See if you can answer those questions now. Your options again are metallic, ionic, covalent, or none, and you can use each of those labels only one time. So here's how I think about this question. I went up to each of the groups and I grabbed the sign of the charge, either a plus, a minus, or a 0. The number really doesn't matter. If I have 2 pluses, like in group 1, that would tell me that I have a metallic bond. Go ahead and write that in as your answer now, metallic. Ooh. And likewise, if I had 2 negatives, that would tell me that I have a covalent bond. If I have a mixture of positive and negatives, that would tell me that I have an ionic bond. And last but not least is the one that we always try to trick you with, which is going to be none. Because H is at 0, aka a noble gas, that element family will not bond with anything on the periodic table, so we just say none. Let's take a look at question number 3. So question number 3 is just like number 2. It's just in a different way of asking it. With question number 3, we want to identify the elemental pair that would create the ratios above. So here's how we would do that with letter A, and then you'll do the rest on your own. Ca is going to be a plus 2. F is going to be a minus 1. When I compare those charges, I can see that I have 2 positives. And I have 1 negative. Well, I need to have the same number of positives and negatives, so I'll add on another negative. And now I have 2 positives and 2 negatives. This is going to create a 1-to-2 ratio. So I would want to say that A goes with number 1 up here. Pause the video now and try the remainder of these on your own. Alrighty, so here is the answers for the remainder matches. So we have M, G, and O, plus 2 and minus 2. When you set those equal to each other, they have the same charge number, 2 positives, 2 negatives. That's a 1-to-1 ratio. That would best put B with template 4 up here. For SR and P, SR has a plus 2 charge and P has a minus 3 charge. Let me show that to you right quick, actually. So 2 plus 2 plus 2 is 6. Minus 3 is 6. Positive, negative, both are 6. That's when you stop adding on. That means we wrote SR 3 times. We wrote P twice. It puts it at template 3. Last but not least, Li is plus 1, O is negative 2. So we have 2 positives, 2 negatives. That's a 2-to-1 ratio. That puts it at D. For question number 4, when you have a diagram like this, remember your first question is always, is what I'm looking at ionic, covalent, metallic? Well, what is potassium? So potassium is represented by element K, and it is going to be an alkaline metal. So that's going to be a metal. S is going to come from the front of the periodic table. It is sulfur. It is on the right side, so that makes it a nonmetal. When you put a metal and a nonmetal together, you are going to get an ionic bond. And once you know that you have an ionic bond, you can name it, you can write its formula, you can tell me about its properties, you can tell me what the electrons are doing in the bond, you can tell me a lot of things. So let's start with what happens to the electrons in this bond. Well, just because it's ionic, we know that it's going to transfer the electrons. And because we know it's an ionic bond, we can name it. The name of K is potassium. Because potassium is an alkali metal, it will not need a Roman numeral. S is going to be an element that comes to the front. So is it going to be a name that ends in IDE or ATE? Since it comes from the front, it's going to change into IDE, which is going to become sulfide. Now we can also address what kind of properties this type of bond would have. Because it's an ionic bond, we would assume it to have a high melting point because it contains a metal. We would also anticipate for it to be a conductor when dissolved in water. And because it will be a conductor when dissolved in water, we would also anticipate it to dissolve in water. So again, these are all going to be properties of an ionic bond. Questions 5 through 8 are going to challenge you on how to name things and how to write chemical formulas. Question 5, which of the following questions should you consider first when naming a compound? The key part of this is which you should consider first. So do I change the second element to end in IDE? No, the second element does not get named first. What prefixes should be used? Is that an element name is that an element question that we would probably want to address? Yes, it could be, but is it our first? No. Is the compound ionic or covalent? Yes. This is the question that we would want to consider first. The entire video and entire review session, I'm telling you, at the end of the day, it is about what you are combining together and what type of bond it will form. You want to start at that very basic question, which is asking, is the compound ionic or covalent? Part 6, what does the Roman numeral represent in an ionic compound's name? So first things first, Roman numeral is synonymous with ionic compounds. We can only use Roman numerals if we see transition metals. And so if we do that, it represents the transition metal's ionic charge. Now you need to remember the charges that go with the Roman numerals. If we have a single I, it becomes +1. Double I becomes +2. Triple I becomes +3. And IV represents +4. Remember, transition metals can have multiple charges. So if I tell you iron, I have to tell you what version of iron we're working with. Is it +2 or +3's version? Depending on which ionic charge we're using would greatly affect my physical and chemical properties that I would expect from that compound. Question number 7. Which question should not be considered when naming the compound CuSO4? So I'm going to take a second and do a little bit of teaching with this question that goes beyond just answering question number 7. You are going to be challenged on this test to take a compound and name it. So how do you do that? I would start by taking the compound and writing it down on my piece of paper. I would underline my first two capital letters, C and S in this case. I'm going to split my compound between those first two capital letters so that everything is broken apart. I'm going to look up Cu on the periodic table. Cu is a transition metal. So because of that, I know that it's ionic. So that is the first question that I would consider when I'm naming this compound. The second question I would have to consider now is, do I need a Roman numeral because it's a transition metal? Now, between our last two questions, which one of these should not be considered at all because we now know that this is an ionic compound? Because we know of this, that means that we should not use prefixes, or we're going to say no prefixes. And because of that, that is the question that I would not consider when naming this compound. So now beyond that question, let's go back and do a little more. How would we name it? What is the name of CuSO4? Because it's a transition metal, it can have multiple charges, so we need to determine its Roman numeral. In order to determine the charge on any metal, you're going to look at the nonmetal part. You're going to look at the negative ion part. That, in this case, is SO4. SO4 is a polyatomic ion. Anytime you have multiple atoms acting as one group, then you're going to have a polyatomic, which is on the back. When you look it up on the back, you're going to see that it's going to have an ionic charge of -2 and that it's called sulfate. When anything ends in ATE, you have to leave it alone. Now, the next thing I notice, how many Cus are in here? 1. How many SO4s are in here? 1. Yes, there are 4 atoms of oxygen, but that's not what I'm asking. I'm asking how many groups of SO4 are in there, and there's only 1. When you look this up on the periodic table, that is how it looks as one thing. If you thought that there were 4 SO4s, let me show you what that would actually look like. If you wanted to say that there were 4 SO4s, you would have to see something like this, where we have the polyatomic ion in parentheses and the amount that we need outside of the parentheses. Now that we know that it's a 1-to-1 ratio, that means that I need 1 Cu to balance out this -2, which means that it will be a +2. Again, because it's a 1-to-1 ratio, I know that I need 1 Cu to balance out my -2, and that creates a +2. Once I figure out what the charge is, I can tell you the name. Cu is copper. Ionic charge of 2 becomes copper 2, and sulfate remains the same. In question number 8, we are going to name or write the formulas of ionic and covalent bonds. I would also do a lot of practice with ionic and covalent naming and writing formulas because that is kind of heavy on the exam. So our elements are zinc and carbonate. Zinc is Zn, and it's a transition metal. So a little hint, hint, wink, wink. Whenever you have a transition metal, the first thing I would do is flip over your periodic table and look on the back, because you might have a transition metal charge given to you. Some transition metals only have 1 charge, and so when that's the case, we can list them in this section. Zn, zinc, is one of those ions. It's always going to be found as a +2, so that means that we can go ahead and assume it's a +2 charge. Carbonate ends in ATE, so again, it's on the back of the periodic table in the C section. So if we look in the C sections, we can see carbonate right here, and it has a formula of CO3 -2. So we're going to write that in. Because I have a positive charge and a negative charge, I know that this is an ionic bond. To figure out the formula, I'll put Zn +2, CO3 -2 beside each other. I can see that I have 2 positives, 2 negatives, so that means that these numbers go away. And that means that we have a 1-to-1 ratio, and that's going to create ZnCO3. To name that, it becomes zinc 2 carbonate. For aluminum and oxygen, aluminum is going to be a metal on the periodic table, so we'll go to the front. Aluminum, even though it is attached to the transition metals, it is the only metal over here that truly acts like a regular metal. So it's adjacent, but it's regular. So aluminum does not need Roman numerals. It does look like Al with a +3 charge, though. Oxygen is going to be a regular element, so that's O, and it carries a -2 charge based on where it is. We have a plus, we have a minus, ionic. We're going to put them beside each other, and let's check out the charges. So here we have +3, and here we have -2. I have a total of 3 positives, 2 negatives. So I'm going to add on some more negatives. Now I have 2 plus 2 negatives giving me 4 and 3 positives. Still no balance, so I'm going to say Al plus 3. Now I have 6 positives and I have 4 negatives. Adding on another negative, because those are not the same number, I now have 6 positives and 2, 4, 6 negatives. I can go ahead and get rid of those and tell you that the ratio is 2 to 3. Because aluminum is a regular metal, it is going to need no Roman numeral. Because oxygen is a nonmetal, we change its name to have IDE on the end, which is oxide. Dinitrogen monoxide. So dinitrogen monoxide contains something that's called prefixes. Prefixes are things that go with covalent bonds. We'll talk about some prefixes in just a second. Prefixes tell you how many atoms of that element are in the compound. So di is 2. So essentially there are 2 nitrogens. That formula becomes N2 then. Monoxide is 1 oxide or 1 oxygen. So that becomes O. That means that in this compound we are dealing with nitrogen and oxygen as our elements. For iodine trichloride, there is no prefix on the first element. That tells me that there is 1. Mono is a prefix that can only be used on the second element and not on the first. Trichloride tells me that there are 3 chlorides or chlorines. So this becomes I1Cl3. Again, because we have a prefix of tri here, we can see that that was a covalent bond made up of iodine and chlorine combining together. Let's pause and talk about prefixes for a second. So prefixes are going to require a little bit of knowledge, but you've been surrounded by them your whole life, all the way up to 10. Like you know that there are 10 years in a decade, so deca is the prefix for 10. You know that there are 5 sides on a pentagon, so penta is for 5. Our conversation told you that mono is for 1 and tri is for 3. You also know that an octopus has 8 legs, so octa is the prefix for 8. Some other ones that are a little more obscure are 2, which would be a di, prefix, 4 tetra, 6 is hexa, 7 is the one that is often missed, it is hepta, and 9 is nona. These are the prefixes that you can use with covalent compounds only. Pause the video now if you need to write them down. Question number 9. So we talked about diatomic molecules in question number 1 of our study guide. And essentially what they are is they are di-2 atomic atoms that are the same molecules. This is the most common example that we will give you of a nonpolar covalent bond. There are 7 diatomics, and they form a 7 on your periodic table in the nonmetal section. I'll show it to you now. The diatomic elements on the periodic table are going to start with nitrogen all the way over to oxygen and fluorine. Then we're going to go down the group of halogens to iodine. And then we'll go back up to connect our 7. Now that's 1, 2, 3, 4, 5, 6 of them. And I told you that there are 7. So the final diatomic on your periodic table is going to be H. This combination of elements creates our diatomic molecules list. So, is phosphorus a diatomic? No. Is nitrogen? Yes. Sulfur? No. Oxygen? Yes. Fluorine is a halogen, so yes. Hydrogen? Yes. Bromine is a halogen, yes. Chlorine? Yes. Argon? No. It's a noble gas. And iodine? Yes, because it is a halogen. This is something that you just have to memorize. A, which are diatomic molecules, and B, what does that mean as far as type of chemical bond? Question 10. On the midterm, you were challenged to look at a data table of a substance and determine what type of bond that substance was exhibiting: ionic, covalent, metallic. You're going to be asked to do that on the test as well. We've given you a data table of 3 unknown solids, X, Y, and Z. We tested their independent properties, and we gathered the data that you see. Using this data, can you determine what type of bond you're probably witnessing, and then match it up to a substance that has been provided for you? Substance X. So it is a white crystalline powder. It is soluble in water, has a high conductivity, has a high melting point. I'm going to make this a little bit bigger. So when we see a very conductive solution with a high melting point, that tells me that I'm looking at an ionic bond. High melting point, high conductivity, very soluble in water. Out of these 3 substances, that is going to be NaCl. NaCl has a metal in it, and that would help me align that with a high melting point. Substance Y and Z, there's a medium and a low. In my brain, I'm going to go with the low, 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 because if it's not soluble and it's very low melting point and it's very low conductivity, that tells me that it is probably nonpolar covalent. Now, nonpolar covalents are going to be made up of only nonmetals. So C20H42 only has nonmetals, carbon and hydrogen. C6H12O6 only has nonmetals over here, C, H, and O. So how do I know which one of these is nonpolar covalent? So nonpolar covalent is one that relies on symmetry. So if multiple things are going to be connected together, it wants it to be the same things that are connected together. And the one that best fits this is going to be C20H42. The only thing in the molecule that would be connected upon each other, creating symmetry, is going to be something that has only carbons and hydrogens. These types of molecules are known as hydrocarbons, and they are the second most common type of bond or example for a nonpolar covalent bond. Remember, it's hydrocarbons and diatomic as the most common examples of nonpolar covalents. In the middle, we have a polar covalent bond. Anytime you see a medium conductivity, a medium melting point, it's polar covalent. Polar covalent is made up of nonmetals only, and they're going to be different nonmetals. And of course, that's going to be something like C6H12O6. Let's go ahead and take a look at question number 11. So we want to fill in the table with the correct information for each bond type. Pause the video now because we've been talking about metallic, covalent, and ionic bonds, and see if you can answer this summary table. Alrighty, so let's quickly go over the answers to each of these columns and see how you did. So the species involved for a metallic bond, this should be metals only. For a covalent bond, nonmetals only. And for an ionic bond, metal and nonmetal. For the electron behavior in a metallic bond, we would describe it as delocalized, creating a sea of electrons. For covalent, we would describe it as sharing, equally or unequally. And for ionic, we would describe the electrons being transferred. Are these bonds soluble in water? Meaning, will it dissolve in water? Will a metallic bond dissolve in water? No. We know that metals like jewelry do not dissolve in water. Will a covalent bond dissolve in water? The answer is, again, well, let's say no and yes. If I'm nonpolar covalent, then that means no, because non means no. But if I'm polar covalent, then the answer is yes. And finally, ionic bonds. One of their key properties that makes them different from metallic bonds is the fact that, yes, they will dissolve in water. Think about table salt. We can make salt water. Think about Epsom salt that can go into your bath to help you relax your sore muscles after a workout. Again, salt dissolves in water. Now let's go ahead and talk about the examples for each of the bond types. So metallic bonds are going to be made up of metals only. When we take a look at this, that would be something like Au and Ag. This would be a mixture of gold and silver, an alloy. And the other example would be something like Mg. Mg is an alkaline earth metal, making it something that forms from metallic bonds. Covalent bonds can be anything that are two nonmetals joined together, whether they are different or the same. In this case, it would be HH, HBr, and O2. Each of these are going to be an example of two nonmetals bonded together. Last but certainly not least is going to be our ionic friends. So they're going to be a metal and a nonmetal together, which would be something like NaCl and K and F. For question 12, we're going to talk about what types of materials can be made from the different types of bonds that hold the atoms together. We talked about everything from clothes to cookware to help you understand how to relate these things. So read each of the material descriptions and classify it as one of the types of materials that we learned about in class. Metallic, ionic, hydrophobic material, metallic, hydrophobic materials, polymers, medicine, or allotropes of carbon. So hopefully you paused the video. I'm going to highlight the part that I think is super important, and then you should write in the answers as I'm discussing it. If a company wants to create a coating for camping tents that is lightweight, flexible, and repels water, the key phrase right here is repels water. That would be us describing a hydrophobic material. 2. Researchers are developing a thin patch that slowly releases an antibiotic into a wound over several days to dissolve once the antibiotic has been delivered. We're talking about an antibiotic, so we're talking about a medicine patch here. Designers want a clear, shatter-resistant, and flexible phone screen. Shatter-resistant means that it is a very durable substance. The one classification that we have linked with durable is a polymer. Number 4, scientists are designing the next generation processors that use ultra-thin, highly conductive materials to transmit signals at nearly the speed of light. This right here, ultra-thin, highly conductive, speed of light, because it's a fast processor, that tells me that I'm looking at graphene, which comes from graphite, which is in your pencil. So this is going to be an example of an allotrope of carbon. And last but not least, if you have an aerospace company that needs a strong, flexible material that conducts electricity efficiently and resists corrosion, that's going to be a metallic substance. Good luck on your chemical bonds test. If you need extra support or practice, please get with a chemistry teacher and do some extra practice with the quizzes that are posted.